We're ready for another week. More chillers, more plants, all the stuff. I hope you're having a great week. I hope you are really enjoying your weekends. This is a tough time of the year. It's a very busy season, and it's important that we try to take our weekends. We were heading to one of the local farms to pick up some peaches over the weekend, and seeing somebody look like they were running an after hours or a weekend call. Somebody was on call to a residence. It's what we do is very difficult. It takes a lot of our time, a lot of our energy. When we're not on call, which for some of us may not be that often, it's important that we really take time to rest and be with family and prioritize our time in that way. Anyway, I hope y'all are doing well. Hope you're having a great week. I hope you've enjoyed everything. And if you're not having a great week, well, then just let's have it. Let's go ahead and get that out. And let me see if I can take your Monday for you. It just make things a little bit better. Something, right? We can try to do something here. We do have some questions in the in the reserve bank that I'm going to be trying to work through. Again, if you have any questions at all, you're more than welcome to throw them in the stream. I didn't have any on the portal for this time around, so we're just going to go, unless somebody has a question they want to dive into first. We're going to dive into the to the bank of previous questions I haven't gotten to yet. So this first one's talking about glycol and approach. So anyway, OYE. You got me on that one. See, here's the thing. I'm of the right age group to know this kind of stuff, but there's a lot of it I don't. I don't know OYE. How you doing there, by the way, Michael? Good to see you, bud. Yeah, you'll have to explain that one to me. Like, I know a bunch of them, don't get me wrong. And I was a part of that teenage era where what do you even call it now? Where you had the little short script text, OYE, mate. OYE, yeah, that's not a model number that I know of. Yeah, I don't know that one. Don't know. Okay. We're going to roll into our first question here, guys. Ooh, and work. There we go. It's not an acronym. It's not. Well, what does it stand for? If that's a model number, it's not a model number I'm familiar with. Yeah. How would someone coming from the aircraft maintenance industry become commercial? So, yeah, let's cycle back around here. From the aircraft maintenance industry. JFC, I'm telling you, man. From the aircraft maintenance industry to the commercial. So, I actually do know a aircraft mechanic here locally. I'm on the fire department with him, and we get to genuinely get into some pretty interesting conversations because from a mechanical perspective and even somewhat a controls wise. Now, I don't know, you said commercial aircraft, so there's probably some pretty serious controls packages on those. This guy doesn't do those larger planes, but either way, there a lot of fundamental breakover is there, like from mechanics and side of it and stuff. And I'm not laughing at you. Frylock here is throwing stuff at me. I'm laughing at him. So yeah, I think they would be. Oh, that's right. We do have an old aircraft mechanic. That's right. I forgot about him. So long story short, I've known a few people at this point who your skills working on aircraft, from the mechanic side of it to the control side of it, you've got to learn the refrigeration piece of this. You've got to learn more about the hydronics piece of this if you're going to get into chillers specifically. So there's aspects of this trade you have to learn. But if you have a mechanical aptitude already and you've already gone through a cycle of having to learn an advanced industry like aircraft mechanics, then it's been my assessment that I don't think it would be that hard to, with time, translate a lot of that over, because you're going to be coming in with just a lot of raw knowledge of just fundamentals of how these things work. That's one of the crazy things about it. There's far more crossover because the engineering, the physics of what we do, the chemistry of what we do, all of that stuff that we do is true no matter the industry you choose. Doesn't matter if it's HVAC, doesn't matter if it's aircraft mechanic. That's not what's important. It's learning those pure fundamentals to begin with. If you get that far, then a lot of those skills very quickly start to translate back and forth between a variety of different opportunities, right? So now you said how. So that kind of comes back to where you are, right? In some areas, it may be better to go union. I get in conversations all the time, especially if it's a heavy union state. Let me say it that way. So I'm in Texas as an example, where we have unions, but we're not a heavy union state, period. So you can operate on the commercial industrial side fairly easily, and you'll run up against the unions as competition, but you're not just shut out from anything because you're not a union, the way that I see that happen in other places, right? So even if you're in a union state, it's not a guarantee you have to go union, but the point is there are some states where that was the easiest choice, if you will. That was the choice that a lot of guys took because they owned most of that industry. So much so of that it just only made sense to go union. So that's what it comes down to: finding a company and maybe doing some research, going through a lot of this stuff on my channel. I've got courses over at chilleracademy.com. Like, I've got a lot of material that can help get you all the fundamentals you need. And if you went into a shop, especially a non-union shop, and you presented that and you showed the effort you've put in to get into this side of the industry and start to work that direction, you're going to have a much easier time getting your foot in the door. And at least you might still have to start off as an apprentice. Okay, so I don't know what your pay parameters are, what your minimums would be. Here in Texas, it's pretty standard that apprentices start off at about 20 an hour now. That's a very, very standard rate. I know that on the union side here in Texas, once you, I'm trying to remember, I think once you hit journeyman and you complete your apprenticeship, which is like 4 to 5 years, you go straight to 30, I think it's 31, 32 an hour, something like that. And then you could scale up from there far above that, 60, $70 an hour in some cases. So, yeah, it's going to come down to where you are, understanding your state, what the market is like in your state, and that may come back to just finding some companies. All right, so here may be a simple thing. Just go talk to a few companies. If you Google search in your city or wherever you're at, chiller service contractors or something to that effect, you're probably going to have some mechanical contractors come up, and they're going to be advertising. We do commercial, industrial, heavy commercial. Like, those are keywords you're looking for: heavy commercial or industrial work, hydronic work, those types of verbiage. If you see that, just call and talk to somebody. or go up to the office and just ask if you could sit down with somebody. You're interested in getting into this side of the industry. You'd like to know more about how things are locally. And that's really the best direction I can point you confidently, because the more I do this on a national and international scale, the more I realize that there are so many nuances to each market that there's not without knowing where you are, there's not a firm cookie cutter, this is your best path forward. And I'm really excited that you're interested in choosing this. The things that I really love about this side of the industry is we are every industry bundled in one. Like, genuinely, electrical, plumbing, mechanical, the chemistry and the science side with the refrigerants. Like, there's just so much, from the controls aspect. We get to do all of that. And honestly, we learn a lot of it to such a degree that it's not that hard for us to compete from a knowledge level with all these other industries who specialize in just the one thing. I'm not saying we know genuinely better, even though I would argue that I think we learn electrical better than electricians learn electrical. Just personal opinion. Anyway, point is, like, we get all of that. It's just such a dynamic trade. It is so much fun. There's so much that happens and goes on. It's always something new and different in an exciting way for me, right? Not everybody likes that, but I know from my aspect, it's just so phenomenal. Yeah. He's great. He's great mechanically. Struggles with electrical and chiller plant processes a bit, but he's great otherwise, yeah. You explain why there is a small condenser on the top of the centrifugal chillers. Yeah, let's do that. Frylock did answer you there, but let's get into that a little bit deeper there for you, AJ. Let's come over here. Let's just make sure everybody's up and up. Give me just a second. And we'll switch over to the whiteboard and draw some of this out. Okay. Can you explain why there is a small condenser set on top of a centrifugal chillers? Thank you. So this is specifically going to be referencing a purge unit. So a low pressure system uses a purge to get rid of non-condensables from the system. So let's say we have our chiller. Okay, here's our compressor, got our suction flange. All right, and then right here we're going to say is our little purge system. Okay, purge. Now what this is doing is, with a low pressure machine, this evaporator can operate as, in a vacuum, right? So -8 psig. I can spell today. Being the fact that it's in a vacuum, that means that we have the potential to draw in atmosphere. Whereas with like a high pressure machine is how we would term that. So low pressure, high pressure. High pressures are going to operate above a vacuum. Low pressures will operate below. And even the condenser on some of these. If you've got say an 80 degrees condenser, you may be floating at a couple of psig in terms of the condenser pressure. But if you start cooling that condenser down, into the 70s, 60s, depending on the specific refrigerant, your condenser is going to run at -1, -2 psig for your condenser pressure as well. So just bear that in mind with these low pressures. This whole machine is just a different refrigerant, right? It comes down to these refrigerants. This is where they boil and condense at. Okay, so being it's low pressure, instead of when we have a leak, refrigerant leaves and escapes the chiller. When we have a leak, refrigerant can get into the chiller instead. Not refrigerant. Atmosphere can get into the chiller instead. So we have the exact opposite issue. That's where this purge comes in. So this purge is a separate little reefer unit, little refrigeration unit that has an independent circuit. Most of the time, so they could be, I've seen them as 404 134A before. I've seen them as 134A. I think those are probably the two most common. Anyway, they're a high pressure refrigerant, and they've got a separate little evaporator, condenser, the whole bit, and a whole little pump out assembly. So what's happening inside of there is we've got this chamber, okay? And this chamber has typically it's going to be like an AXV style metering device. So MD for metering device. And that's going to be feeding off of the little refrigeration circuit. You have a little pot belly compressor, a little piston in there pumping its little heart out. So we go through the condenser. We hit our metering device and into this evaporator. And this evaporator is going to have a coil. So it's just going to be an evaporator coil that comes out and then comes back into the suction of our little compressor. It's a closed circuit refrigerant system at that point. Now, outside of the coil, on the shell side of it, if you will, if you want to take that concept, we're going to pipe that into our condenser, specifically the condenser. And we'll have another pipe coming out the bottom with a little like catch assembly, and that's going to also come back to the condenser. What we're doing, and this is a very basic view of this, okay? This gets far more in depth, and we can if you need to. But essentially, from a very high level view, we're creating a natural draft situation where atmosphere is not going to condense, but we can condense the refrigerant. So as the refrigerant fills this cavity, we will cool this evaporator coil through this refrigeration process. And the refrigerant, the low pressure refrigerant, will condense and collect as a liquid down here in the bottom. As it does, that liquid will naturally gravity feed down, and that's why our purge units are on top. They're above the top of the condenser. This so that that liquid can drain back into the condenser via gravity. Well, the thing is, as this liquid is draining down and flowing back, it's basically siphoning in more vapor into the chamber. And it creates this self-feeding cycle. The refrigerant condenses into a liquid, drains out, it pulls in more vapor, and it continues this process. And as it does this, any atmosphere that's in there will continue to collect in this chamber. Now, eventually enough atmosphere collects in here that via a couple of methods, we will determine that we need to go through a pump out. All right. So one method would be we're monitoring suction superheat here with a temp sensor. So we'll see that our suction line temp on the compressor got really cold. Why? Well, because we don't have enough load on here, so our superheat drops. Now, that's one method. Another method would be we have a transducer reading pressure on this chamber. And this transducer is comparing this chamber's pressure to the condenser pressure. And when they get so far apart, specifically this chamber starts reading a higher pressure above a certain threshold, we know that we've got enough atmosphere stacked in here, it's time for a pump out. All right, so those are a couple of different common methods that we would use to determine how much atmosphere is in here. Then the machine goes, okay, it's time for a pump out. We are then going to take a separate little pump unit. This kind of sits up here. All right. So this pump is going to have a line attached to the top of this chamber, and it's going to draw out and go through this pump and out into atmosphere. All right. Now, again, the cycle does get far more complicated. If you then get into a secondary chamber called a regen tank or a capture tank that goes into trying to get more of the refrigerant out, not push it into the atmosphere. Like there's more to this, but from just a very basic level, we're just going to draw off the atmosphere from this tank, push it through this pump, and push it back outside. Usually it'll feed into the venting system for the chiller itself. If the rupture disc or something was to break and the system needs to vent out, this purge line will be connected into that so that it flows back to the outdoors and it doesn't push all that into the actual chiller space itself. So yeah, once it gets enough of the atmosphere out of here, either this pressure in here will drop enough that we could get we're going to drop back below a threshold, or we're going to do a timed pump out and then recheck on our pressures, or our suction superheat on the compressor is going to rise high enough that it's going to tell it, okay, I've got enough atmosphere out. Let's stop the pump out cycle and let's go back into a normal, just normal, not purge, a normal operation, right? So where we're not trying to pump out anymore. And this whole process, this little compressor here never shuts off during the pump out phase. It's constantly running this whole time. So yeah, once we stop the pump out, we go back into normal, and we will continue to just condense more of that refrigerant down, stack more of that atmosphere, and this process just continues. Now, if there's very little to no atmosphere in the system, then this little purge unit can just run and run and run and run, and it just never needs to pump out. It never becomes an issue. But you'll know, one of the first ways you'll know you have a leak on a system like this is you will start to have really high pump out times. And that's part of what these machines are monitoring for, is how much time do we spend in a pump out. And if we start to spend an excessive amount of time pumping out, then we know we've got a significant leak or condition going on, and we need to dive in a little bit deeper. Anyway, like I said, from a very high level perspective, I go over this really in depth and in detail in the certification course at Chiller Academy. So if you do need help, or you want to get deeper into how these types of systems work and better diagrams of them and such, I would encourage you to just go consider that course. And it's going to be in the centrifugals module. That's where you're going to find more information about how these are working and more specifics on their cycles and what's making them function. And this is going to be something important to know, because we are getting back to a lot more low pressure machines. Now that we've got, 514, I believe, is going to be our new low pressure refrigerant. 514 and 1233 ZD, I think. I think those are the two, if I'm pulling it off of my memory correctly. Either way, those are our new low pressure refrigerants. And so that's what York, that's what Trane, that's what Daikin, that's what all these guys are going with now. And we had a dip in the industry where Trane was one of the few people who had a low pressure machine and was using that. But now that we've got these new refrigerants come back, low pressure machines are making a comeback, which also means learning and understanding these purge assemblies is going to be essential, because they're a major part of that low pressure system, and we really got to understand it. And it's not just going to be a Trane thing anymore. What's nice about it, though, this time around, is they're all using a very similar design. See, in the past, York had like the YT series, but they had I did not like their low pressure system. I don't really know anybody that did, or in terms of their purge system specifically. So like with Trane, we're using the Earthwise or Ready Purge types of systems. Those were far superior. And a lot of us, we would retrofit a YT to a Ready Purge, because they were just, the factory system was just such a pain. Anyway, most of them that I'm seeing are those newer styles of purge systems, and they're much easier to work on, much easier to use. So that's what, it's really important that we actually get a grasp on this stuff. The sooner the better, if you're going to take doing chillers long term seriously. Just say we're better than everyone else. It's fine. Yes, absolutely. I agree with the electrical statement. Yeah, absolutely, man. I hope you find your way in the from the aircraft side over here to the chiller side. We'd love to have you. Compressor. So I'll come back to you there, Michael, in just a second. Let me catch up on some of these. Explain how purge unit works in auto. Okay, I can come back to that. A little vacuum pump there. Wrong CT ratio. Yeah, Keith. Yeah, yeah. There's a couple of solenoids depending on this particular model you're dealing with that help control that pump out cycle and make sure we don't have leaks and whatnot. Because of, yes, absolutely, AJ. Yeah, a low pressure compared to atmospheric pressure. Yep, absolutely. One, and it lost 100 pounds of refrigerant. Yeah, that's the reason why I bought it in on the convert. Yeah. Yep. Okay. YV compressor RLA on the Delta plate read 146 compressor 1 and compressor 2. When I check VSD menu, I show 131, 61%. Why do I not show closer to the 100? 117, 66. That's a good question there. Okay, well, I'm going to put this one up, and maybe we can just kind of brainstorm through this one. Okay. All right, so let's think through this. YVAA compressor RLA on the data plate is 146 for compressor 1, 117 for compressor 2. When I check the menu, I show compressor 1 at 131 amps, compressor 2 at 110. 66 FLA. Why do I not show? Well, both of those are showing low on FLA compared to if you're going to do like a linear math. It's what I mean. Like from a linear perspective, they're both low. Why do I not show closer to 100%? Well, Tom had mentioned a CT ratio, which on a YVAA, we don't have the ability to manipulate that from the programming side. That comes from the factory. So if that would be wrong, you would be arguing for a firmware problem. Which I do think you're right on that, Tom. It is an actual ratio that they're displaying that number through. It's not literally linear math. I don't believe. Why do I not show closer? I'm just trying to think through. Chiller over. I'm on site currently. Let me know if okay. Also, data plate isn't always accurate to what's inside the unit. I've seen 208 unit with 460 compressors. I can only wrong order. Is he looking at the CTI? Feels like a weird setting or something still, though. I mean, yeah, with being that close. And so, are you looking at this from the all right, so we get to do a real live on-site troubleshoot here, guys. Are you looking at this through the status menus? For I guess it would no, you're looking at this through the VSD menu. So you're on the VSD menu inside of that screw control panel. And you're pulling up the yeah, because it does display the FLA like that. Yeah. Yeah, interesting. What's your hertz at? Okay, here we go. What are your hertz at by chance? Please check actual amp by clamp meter and compare it to display CT ratio or anything. Well, not really any problem. Just curious. Right. So, yeah, I would be curious. What is your hertz reading currently? Show that out 83 hertz on a 200 hertz motor. Uh, 83 hertz on a 200 hertz motor. We're at 60% FLA. Okay. Yeah, because I think those at the bottom end will ramp down to like 40-50% at, what is it, 50 hertz is the minimum speed on those? Check percentage change. Yeah. He's not having a problem, everybody. Just to clarify, in case there's any confusion, it's not that he's having a symptom. He just noticed that's weird, right? Because from the data plate to the actual, like the math ain't mathin', and so it's a good question. To be honest, I don't know. I don't know why it's showing that. And I'm wondering, going back to the calculation thing, right? So Tom, Froggy may be onto something there with. I wonder if there's some kind of internal like load calculation happening where sure the amps are high depending on what your condenser pressure and your evaporator pressure and how you're controlling that refrigerant flow. That's going to have an impact on those amperages. Which for that low of an amperage, like that high, or I'm sorry, for that low of a hertz, you're having high amperage readings, even though you've got a low hertz, and your FLA lines up with the hertz. That's part of what I'm thinking about is your actual hertz value of 83 hertz lines up with 60 something percent FLA. I would have expected that. Now the 130 and 110 amps at that hertz compared to what the top end is supposed to be does feel a bit heavy. So it's got to be just a math thing on the ratio. However, whatever parameters York is looking at to make that calculation it knows that, okay, I'm already at this amperage, but I know that based off of this hertz and whatever these load conditions are, I'm actually only pulling 61% of the full load amp capacity that I could be pulling if it wanted to stage up. That would be my next assessment, kind of going along with the, like what Tom was saying, where it's got it's a calculation thing maybe. And close to F, I was right. So now maybe partially because we're trying to think of it in a linear math format versus it's being an actual calculation based off of, say, hertz speed and amperage, things like that. That would be my next best assessment that I would offer. If I had to truly take a swing at it and try to justify it, that would be, I think that'd be the direction I'd go. Compressor 1 overload is set to 225. Compressor 2 175. Check the battery in your meter. It's all overcurrent. Sorry, I found the VFD for the condenser fan is getting intermittent overcurrent faults. Which the condenser fan, you may have a fan motor starting to go bad because on those YVAAs, they all run off of a central. Each circuit's condenser fans run off the same drive, so it's possible that one of those fans may be intermittently failing, and it's causing that whole drive assembly to trip out because they've got those ABB drives in there. At least the last ones I looked at, that's what they were using, was what were they? The 500 series, 550s, 580s, ABBs. Yeah, I need to isolate and check individually, yeah. Okay. But anyway, that's my best shot at it. I'm not sure what your actual problem is. Well, not that you have a problem. Let me rephrase. You don't have a problem. I don't know what the correct answer is. How about that? Okay, let's explain. So this question from Kiran, sorry if that's not how you actually say that, is going to, we're going to dive into the different modes you'll run into. And I'm going to take this from a train perspective, just because that's the one I'm the most familiar with, but we should be able to communicate what we need to with that. All right. Explain how purge unit work in auto. So we've got a few different modes we can work with. Let's come over here to the whiteboard. We have auto. We have just stop or off. That one's pretty self-explanatory. We have adaptive. And then we have well, you wouldn't have a regen. That would be a state you would go into. We'll talk about regen. Just to make sure we cover it. Regen. Which is supposed to be like regenerative or regenerate, whatever. I'm just summarizing. Anyway. Alright, so in auto mode, what we're going to be doing is, if chiller is on, then the purge unit is going to be running, which means compressor is online, or the purge compressor is on, as long as the chiller's compressor is on. So if we're in auto, the purge runs when the chiller runs. So it really is as simple as that, which means the pump out cycle, all the normal internal cycles it will go through, pump out, regen, all of that happens in this auto. Now stop is just going to be a hard stop. So if we've got the purge and stop, that does mean that it doesn't matter if the chiller is online, doesn't matter what's happening, this purge compressor is not going to be engaged. It's not going to be brought online for any reason. There's reasons to do this if you're doing maintenance or service, or if you're trying to test something. Like, either way, if I have a chiller that maybe not be all that tight or I don't really trust, I'm going to run an auto. Now, if you have a machine that is very tight and you do trust, then you could consider adaptive. So adaptive is where it runs on a timed cycle and it's not based off of whether the chiller is actually on or not. So this one here can actually operate even when the chiller is in a off cycle. So essentially what it will do is every 4 hours or so, it will bring the purge compressor on, and it'll run that compressor for a period of time. I don't know, it's 20-30 minutes at least, something like that. And what it's trying to do in that process is, okay, does it stack enough atmosphere to need to go into a pump out? Now, if it does need to pump out for any reason, then it will continue the pump out cycle as needed until it meets some threshold. I don't really remember off memory what that threshold is it's looking for, but it's going to try its best to meet that pump out demand. Now, if none of that is true, then it's just going to run for that minimum period of time. It's going to pass the test, if you will, where it didn't need to do any kind of pump out. And then it's just going to turn itself back off for several more hours and then come back on. And this is just another efficiency thing. It's yeah, it's just removing another load from the compressor, from the chiller, to where we're not having to always have this circuit on and running and trying to pump and move refrigerant through it. So those would be your three main modes: auto, stop, or adaptive. Now, when we go into a regen, this is talking about a regen tank. Let's kind of draw that circuit a little bit. So I'm going to draw it from a pump out perspective. So we have our purge evap. Okay. Then we're going to go through our pump. So we have our pump. We're going to come out of our evap into the pump, and we're going to come out of the pump into our regen tank. And then out the regen tank, we come out and go to atmosphere. And there's solenoids in here and stuff, right? So, and there's other piping in here to configure this. But essentially what's happening with this regen tank is it's a carbon filter. So what happens is, as we're pulling this atmosphere off, there will be some refrigerant that gets drawn off with that atmosphere. It will not be pure, just strictly atmosphere. It won't be free of refrigerant as it gets drawn off. So one of the things we've tried to do is we'll put these carbon filters on the other side of it. Now, a regen system has the ability that we can capture the refrigerant in this filter and the carbon. So the refrigerant molecules will bond to the carbon inside of here, and the atmosphere will continue to flow through. Now, after so much runtime, we do need to engage this regen. We need to recover the refrigerant that's inside of this regen tank, and we need to get it out of this carbon. So how we do that is we isolate via solenoid on this side, and we have another line that, instead of going to atmosphere, it goes back to the chiller's evap. Okay, so the chiller's got to be online for this to work, because we're going to use the chiller's low pressure evaporator to do this. So we're going to actually keep all of this is going to stay isolated. All we're going to do is we're going to engage a heater inside of this carbon tank. So there's a little resistive heater that sits in here, and we're trying to get it to like 220, 225, 245, something like that. It's quite warm, but we're trying to get that carbon heated up enough that the refrigerant trapped in it will basically off gas or release from that carbon, and then we can draw that refrigerant back into the evaporator. And so that way we minimize how much refrigerant makes it to atmosphere. But the original versions of this system, we didn't have a way to recover that refrigerant back. It just got lost in the carbon, but at least it didn't make it to atmosphere. The carbon just captured it as like a filter. With these systems, we can actually get that refrigerant back into the chiller to make good use of it, instead of it just getting sucked away and then just lost forever, kind of a situation. So if you see your chiller go into a regen cycle, this is the basic process of what that regen is doing. So you could have, basically it's just an auto where it's just running, or the compressor is just on, right? So you're in a purge cycle. Then we could have a pump out cycle. So a pump out is when we actually engage our little vacuum pump that draws the atmosphere off. And then we could also go into a regen cycle where we're trying to recover that trapped refrigerant back out of that carbon. So those are your basic operating modes of a purge unit on a low pressure centrifugal chiller. I say 6 fans on one dry. Yeah. Who is the manufacturer of the VFA? It's an ABB. It says, say it like an Englishman. Oh, is that okay? I think I know what you're referencing there now, Mike. I'm not going to try, but I think I know what you're referencing. I can't remember the code. Under, it gives you a 10%. So I think that was the. All right. What is the best way to diagnose a chiller? Using a log sheet. Best way? What data is more critical? This is a really good question. All right. What is the best way to diagnose a chiller? Is using a log sheet the best way? What data is more critical? I think a log sheet is very helpful, very beneficial. Eventually, I find that early on, I would have a piece of scratch paper, and I would go through and I would write down my readings as I went, trying to keep track of it all. Eventually, with enough time, I got to the point where I was able to just remember the key data points. And actually, it's surprising, I got really good with just remembering numbers. Like, even to this day, I can remember numbers really well. Maybe not a whole lot of other stuff, but numbers just stick in my brain. And I think being a technician trained that on a large scale. So, starting off with a log sheet, though, is a great way to visually see your data. And when you get into a situation where you're trying to process it mentally in your mind, sometimes it can be a complex enough thing where it becomes too much, right? And seeing it either on the panel, but the problem with seeing it on the chiller panel is the readings are constantly variable. They're shifting and adjusting. And again, if that's something you're not as confident with, or you're not as practiced at, that may be really disorienting trying to troubleshoot through that. So having a log sheet where you just go through and you just quickly take a snapshot, if you will, of the entire system. And what I've actually done with this, instead of a log sheet, I eventually just started using my phone. What I would do is I would literally, and I would do this on PMs too if I was doing a maintenance, because when I capture the data from the chiller, and I'm going to take a snapshot like that, I want as close to a instantaneous snapshot as possible, because if I'm taking a long time writing all this down as I flip through screen over screen, a lot of changes can happen by the time I start the log to the time I finish the log. So that's one thing I liked about doing the picture method, was I could basically get one hand prepped to hit the buttons to cycle the menus, and the other hand on my pictures, and I could just tink, 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 cycle through that as fast as possible, get all the pictures, and then I had a complete picture within a few seconds of each other of that entire chiller's operating data, right? And then I would sit down and I would take the time to fill out my logs if I needed to from a PM perspective. But from a service perspective, what this allowed me to do was it allowed me to take a step back and actually thumb through and really read and look at the data. And the data is not shifting and moving on me. And so, because I do fall into that trap, or if the data is constantly fluctuating, I'll get sidetracked on trying to chase how the data is changing versus just reading what the data is telling me. And data analysis is a huge part of what we do, and it's a huge skill that we have to have as a quality technician. And I've got a solution for this. There's going to be some stuff coming very soon where I've got an idea on how we can try to work on this and improve ourselves from a data analysis perspective. But it's too early to talk about it too much yet. But I've got some things in the work on this. And it's going to really help you understand how you, like what data and how you can capture data and really analyze it effectively. So in terms of if I'm not going to do it in my head and I'm going to say use some static numbers, that picture format has become my preferred. Like if I truly need that to process what I'm doing. Now in terms of what is the critical data, that kind of comes down to what you're working on. But here are the must-knows for me, right? So it was going to be my chill water temps. All right, that's entering and leaving. I want to know my differential. This is just going to help me indicate load on the machine right there. So I want to know my chill water temps. I want to know my condenser temps on the here. If I have a water cooled, how about that? If I have a water cooled specifically, I want to know my condenser water temp. This is going to help me indicate what, say, lift conditions I may have, even if it's a scroll or a screw water cooled. Now, if this is an air cooled, then it's going to that would just mean ambient. Okay, so CWT / ambient is what I'm trying to say there. That's going to help me understand what it'll look like on the condenser side. And these two together are going to play a big part into what I expect my compressor to do in terms of readings. And what I mean by that is, okay, if I have a high load, I'm going to expect the compressors to be more loaded. But at the same time, I can have a mild load, if you will, but if I have a really high condenser water or ambient conditions, I'll still have high amp draws because I'm having to compress my lift is high. Not even specific to centrifugals. I just have a high lift that's going to require additional amperage to overcome that lift in spite of my load. Put those two things together, right? So this is huge for me to understand what I expect my compressors to do and how many compressors I expect to do it. Beyond that, my saturations, my superheats, and I say superheats specifically because I'm referencing suction superheat, discharge superheat, mostly those two. So I want to know what both of those superheats are. That's going to give me a big indication on what's happening. My saturations are going to lead me into my approach. So what I really want to know my saturation for is to get my superheat and get my approach values based off of the water conditions. This right here can give me a huge picture into what's going on, if it's a water side problem, if it's a refrigerant side problem, mechanical issue. This gives me so much information. Now it's about how do you use this information? How do you apply it properly? Because there's a million variables that each of these data points can register as. And then it comes down to, okay, well, what do you do with that data point? Because if you have a high approach with a low load, right, that's going to tell you something really odd is happening. But if you're also dealing with a low superheat, you've got to say a low approach or a normal one, but you've got a high load. Okay, well, that's kind of weird then, though, because with a higher load, I would expect approach to increase and I'd expect superheats to increase. But if I'm low here and I'm low here, but I'm high here, that's indicating to me that something strange is happening, and it may be a flow issue. It may be a heat exchange issue, because at that the chiller may be struggling to bring the heat into the refrigerant because of, say, fouled tubes, something along those lines, right? Yeah. So right here, this gives me, like, if you were to give me nothing else, just give me this. What's my chill water doing? What's my condenser doing? Whether condenser water or ambient conditions. What are my saturations? And what are my superheats? And if I have these three, then I can figure out approach, right? And then that saturation specifically, it's not just about approach. It's seeing where are we at in terms of saturation. High sat, low sat, and how that compares to our waters or ambient. And then that superheat gives me a final indicator on where our compressor is at. So like on a centrifugal, you're not going to get much in terms of superheat for most centrifugals. There are some that do monitor that. But you're dealing with more of a discharge superheat. And with a screw compressor, you could be dealing with either or pretty equally. And then most of our scrolls, we're more focused on suction superheat. We don't pay as much attention to discharge superheat, but it is still an important factor. So back to the core question. What is the best way to diagnose a chiller? It's specifically using a log sheet, or it comes down to your ability to analyze the data. A lot of that's going to come down to pattern recognition and being able to understand that, okay, when I see these set of parameters, it should lead me in this direction. Don't fall into a trap of basically parts changers, right? So you could argue that a parts changer, it has just learned pattern recognition, and that, okay, I see these symptoms, I put this part in. That would be that's what you want to be careful of not doing from a data perspective. And we can do that, because then we will end up diagnosing things. You may jump straight to, okay, well, it's a flow issue, or you may jump straight to, well, it's a charge issue, or whatever else, right? So we have to learn pattern recognition without falling into the parts changer mentality, because we're not being careful enough with our data. Yeah. Does that actually make sense, or does that feel helpful, Sanchez? Like, is that something you feel like you could use? How about that? Maybe a better way to phrase that. Yeah, exactly. Water is the chiller's version of air. And I mean, you want to get crazy, like very specific scientific. They're both fluids, okay? Just one's a gaseous fluid, one's a liquid. Other than that, like, so many of the same flow characteristics and properties, and like, it all translates. It's just one's liquid, one's vapor. That's really the only true difference. And how that interacts with our machines, it's all the same concept. You'll have similar symptoms for low water flow as you would expect to see with low airflow. If you can diagnose a low airflow situation on an RTU or split, you could probably diagnose a low flow situation on a chiller. One thing that kicks everybody in the butt with chillers is we have variable capacity compressors in a way that we don't see with RTUs. And that's part of why VRF kicks everybody in the butt, because they also have variable capacity compressors. So it adds this whole nother dimension of control and staging and symptoms that you wouldn't see with an RTU with scroll compressors, because they don't have their constant speed. Even if they have a variable speed compressor, most of those compressors are constant speed. And if you want to make an argument for it being different and struggling, that's the real difference. Is the compressor's ability to vary its own capacity. That one variable, while a big one, is the only major difference. Everything else, completely translatable. My TurboCore compressor got sweating at card side and at bottom side. Is it common? No, that is not common. You said sweating. You need to check your cooling solenoids. Here, let me. So this can be a big deal, and I don't want you to lose a compressor. Let me get to my photos here. All right, just give me 1 second. Let me pull up. I'm gonna physically show you what I'm going to talk about. Trying to find the right picture. This one will work. Okay. Flip this around. So, here, let me do this the right way. Let me get everybody on the same page so that they know which one we're talking about. Wrong button. All right, my TurboCore compressor got sweating at card side, so the back plane, and at bottom side. Is that common? So there's two major conditions I'm concerned about there. One would be these cooling solenoids. So this compressor uses, right here is the injection ports for it. There's be a liquid line coming in from the condenser, and it's going to feed into the shell of this compressor. And then you've got these cooling solenoids. One's for the motor, one's for the electronics. This is what we're going to activate these in order to maintain our temperature in here. So the electronics one is going to specifically serve the power side up on top, where the main VSD, the inverter, the capacitor, the SCRs, all of that up there is. And the motor one is going to actually feed the actual motor cavity to keep the stator from overheating in the process. So this is how we're maintaining our motor and electric temperatures on this TurboCore compressor. What can happen though is, one, these valves can fail and they'll overfeed. Another thing is you may have a temperature sensor either on the inverter or in the stator that has begun to fail, and that's going to start forcing these valves to stay open. And you'll have to connect with an SMT tool, unless you're dealing with a Daikin. Okay, so let's see. Daikin and I guess Kiltex or an MCS, like depending on what your control panel is, you may have some of this internal data inside of there. You may not. So that'll be something that you will want to verify. But if you do have that data without having to hook up SMT, so Service Monitoring Tool by Danfoss, then see what your temperatures are showing. And you may have a temperature that, even though you're sweating on the compressor, uh, you may actually have a temperature that's saying it's really hot. Now, that either means, let's say if it's the inverter, that either means that inverter has truly failed. You got a Corel Pico 5. So you're dealing with a Daikin then. So if you've got a Corel controller, you've got a Daikin, this would be a WMC series then. Depending on, you said Pico 5. So you should have a newer series. Yeah, you should have the newer one with an HMI. So you should be able to see, if you go to the compressor screen, I don't have that right offhand to show you, but if you go to the compressor screen, you should be able to see the temperature data inside of this motor for at least the stator and the inverters specifically, and see if there's a temperature in there that is high. Something, if none of those temperatures are hot, then one of these solenoid valves themselves may have failed. So right here, this little, you may be able to read it, says cooling. This Molex here is what feeds these solenoids. This is what's keeping all this cool. So that would be my very first stop is, okay, why are my cooling solenoids feeding, or are they feeding? The alternative would be the suction superheat issue coming into the nose cone of the compressor. Now, the thing is, these compressors are monitoring suction pressure and suction it's monitoring those temperatures coming into the compressor. So if it was having a really low suction superheat issue, I would expect this compressor to catch that, unless the sensor itself has maybe failed or gone bad or is having trouble. It's my experience that this is going to be my first stop. Like I said, the first thing I'm going to want to look at is, what are these doing? Because that sweating, unless you're just in some crazy humid environment, which maybe is possible, that sweating, it means that this is cooling down too cold on the body, and you're going to cause these cards and this backplane system to fail. That's going to end up failing because of that, and that's a big deal. Like, you don't want, I'll just leave it at that. It's a big deal if this fails like that. So I don't want to see that happen. This would be the very first thing I dive into. And if this did actually check out okay, then I'd come over here. And if you haven't seen it before, there's a turbo tool. See, let me pull it up here. Okay, so this is Danfoss's turbo tool. I would highly recommend you pull this up, and maybe you can use this to help troubleshoot. So we go verify service side. We want to, cooling coil solenoid verification. So you could pull these up. That's not really what I would be looking for though. Temperature and resistance charts. This is what you can use to see what your cavity sensor, suction and discharge sensors, right? So these are these sensors could be what's causing that high temp. These are the sensors you're going to want to verify. This is Turbo Tool by Danfoss. Come on. Or we can get into the service side. What do we have in here? Yeah, no, these aren't what Anyway, they also have some documents. They have these videos in here. So if we needed to, backplane, DC bus, inverter, temp sensor, soft, motor, PWM, inverter, SCR. It's like this one. So I'm not going to actually play through the whole thing here, but my point is just kind of show you, like, these would, if you're not familiar with these compressors, pull up this tool, download it. I'm using Android. I know they've got it on both platforms. They'll come in here and they can actually guide you through these different steps and trying to check these things. So yeah, I don't want to lose your compressor. I think that's where I would go, and I would do that as soon as possible. As soon as possible. That concerns me. Mm-hmm. All right, how to diagnose low charge on centrifugal chillers? What symptoms are dead giveaways? What are signs? What are signs most subtle? Use 19XR as example. Low charge. Symptoms are dead giveaways. Yeah, let's talk through this one. Mike, those 19XRs are whipping you, aren't they, bud? I know you've had quite a few of them recently. It's okay. They're not my. They're that I don't. I'm not a fan, personally. Like they're one of my least favorite centrifugals on the market. How to diagnose low charge on centrifugals? What symptoms are dead giveaways, and what are signs are more subtle? Use a Carrier 19XR, for example. So in a 19XR, you've got a float valve assembly. You're gonna have trouble. Trying to remember what all a 19XR would have on it. From a general sense, what I'm going to be looking for is I'm going to start to see high approach values on the evaporator, because the evaporator is going to start running low liquid levels. So yeah, I would expect to see low liquid levels. I would expect to see the inlet guide vanes they're going to start running more closed, and you're going to start having trouble maintaining the load, because your suction saturation is going to be running lower. You're going to start running into a lower suction limit, and I don't remember what all the parameters an 19XR has on the expansion chamber coming off feeding into the condenser, because it's got a float valve for a metering device. I can't. Yeah, I'm drawing a blank off memory for that specifically, but like those would be some just very general things I would be looking for. High evaporator approach. I would expect condenser approach to look really good all the time, even under load. I would expect to see a really low condenser approach, just because there's no refrigerant in there stacking or anything else happening at that point. So it's going to be really easy for that condenser to maintain. You're not going to be building up head pressure as much. You're going to see the IGV is going to struggle with not really wanting to open, because the suction pressure is getting down, and you're going to start pushing into that suction limiting window. Now, if we're talking a minor if we're talking a minor situation, then it may be really hard to determine that. Yeah, it's going to be really hard to determine that, because of, like, you don't have any sight glasses, and it's similar to trying to diagnose that on a train. You're going to have to do your best to go off of the data you have. but you're not going to have a window into the machine. So, this is yeah. So I'm just trying to think through like something I could give you as like a dead giveaway kind of thing of, okay, well, this is for sure. Like I said, but by the time it becomes enough to where you could just easily say, oh yeah, definitely low charge. You've got a pretty severe charge issue at that point. Your discharge superheats up. You're pushing into a suction limiting. Your suction approach is up. You've got low condenser approach. Like those would be things of, okay, if I saw those conditions, that's a dead giveaway. And you're pretty far down the road by that time. You're talking, you've lost 40, 50 plus % of your charge, and that machine's struggling to stay online at that point, and you're probably not making you're probably not making leaving water set point. Now, could you surge at low load? So you run into more of an issue with sorry, I'm contemplating through the choke and surge, which direction I would recommend it. You could surge, yes. You have the potential to surge because you're not able to get your flow up, right? So this may be an early symptom of it. So let's come over here to the whiteboard. Let's just make our surge curve real quick. So we have our lift, and then we have flow. Okay, so this is through the compressor. And then we have our surge and our choke. So part of what will happen is, depending on like early, more not low loads, more like early during startup. Well, you can have it in low load, okay? So I'll finish that line of thought, and then I can follow back around. So we may have a situation where because of our condenser water, we have a set lift, and especially if we are dealing with a low charge condition, we are going to start to see our saturations drop and our evaporator approach increase, which is going to increase that lift as well. So between condenser water set point, which is limited, or condenser water temperature, which is limited to our wet bulb conditions, and then what our evaporator saturation is, that may mean that our lift is set here. But the thing is, we may be operating right here in terms of flow. But as we lose charge and we start having charge issues, our flow condition is going to shift over, because we can't, our lift isn't necessarily changing, but our flow through the compressor is. And this is where we end up over here, where we're pushing into a surge condition, because we don't have enough lift and flow through the compressor to put enough velocity on it in order to overcome that surge condition. So this would be a way to where, depending on what your lift is, we end up in a spot where a charge issue becomes a reduction of flow, and that reduction of flow would push us past that surge boundary, which would then lead you into a surge. Now, you said that more like early during startup. So a low charge causing like early during startup. So every time you go into a startup, then you're going into a surge. If you're losing refrigerant, you're going to have atmospheric pressure in the condenser barrel. Cause it to trip high pressure. Yeah, within a couple of minutes of startup. So if you're what I'm hearing you right, we get through the startup phase, right? It doesn't surge in startup, like in the process of ramping up to speed. But once we get to speed, we start to stabilize, and then a couple of minutes later, we start having a surge happen. Well, that's going to be right as we try to start loading the machine. And that's going to come back to our parameters. What is the process of what is our water temps? What are our approach values at that time? Okay, all right. So basically a couple of minutes in, that's when you're going to start to try to load. So as soon as that IGV begins to try to open, that's when you're going to get into you start to get into a surge. Yeah, while almost completely unloaded. I mean, yeah, unless you have an impeller issue, I would say you could say that you may have a charge issue. So at that point, so what are your system conditions? All right. So what I'd like to know is, what are your chill water temps? That's a W for sure. What are your condenser water temps? And then I'd like to know what your saturations are. If you can give me those at a bare minimum, that'll give us something to try to start seeing. And what I'm asking is, I want to know what these are before it starts to surge, specifically, because as soon as it tries to open and it goes into a surge state, we will end up then the numbers become scrambled and they're just almost useless. So we need to see what these are before we start surging. So I wish I had there was another tech who is checking it out, but then the customer just ordered a temporary. Okay. I mean, yeah, charge is on the table, right? If we had that data, we could see, okay, if we're already pushing the limits or if we're well within inside the limits. So here's the thing. If you're well within inside the lift boundaries, the chiller shouldn't be showing any kind of surging conditions at these numbers, but yet we are. That could mean an impeller issue. It could, or you could have a charge issue. And it goes back to the condition and the history of that particular machine. Like what are the risks that it had a bunch of touchdowns on the impeller, and now we've got part of our impellers screwed up in there, and so then we can't compress properly anymore. And so it's not a charge problem at that point. If you're really, really worried about a charge issue, then just doing a charge check by pulling off, not all the way, don't go to 0 psi, but just pull off majority of the charge, get it down to a couple of psi, and see what your see what the charge is, right? See how much is in there. And that's going to give you a really good indicator if that's the problem. Because if you verify charge, but you're still having a condition like that, and the chiller won't run beyond that really low point, like just as soon as it goes beyond that, it goes into a surge. It's possible that it may have been having a surge problem, and that impeller could have caused an issue, and then like it just had too many touchdowns, and it just tore the impeller up. This is the one where we lost all 1,300 pounds over the course of a month and a half while temporary was in place. Okay. So y'all made the repairs. You put the charge back in. So you know it's not a charge thing then, right? Because you just finished putting the refrigerant in there to charge it. So if you, at that point, if you know it's not a charge problem, you know your refrigerant's in there. I mean, it'd be hard not to question that impeller. And depending on what that thrust bearing's condition is, if that thrust bearing was wearing out, it may have allowed touchdowns, and that high speed machine, that aluminum hits that steel housing, before it lost charge. Okay. Well, again, we circle back to the same kind of thing. If those vanes in the impeller get damaged, you're not going to be able to maintain lift. The only solution for that's an overhaul. So essentially, in your position, this is where I take a step back and I just cover all my basic bases and cover everything that would revolve around a surge condition. What is my lift? Is my IGV where I expect it to be? How are my currents doing? What are my approaches doing? Do I have the flow? So from that point, if all the basics are there and we're still having this condition, one of the few defaults I have to go back to is just condemning that impeller, which at that point, the only way to know that for sure is to begin the overhaul process, unfortunately. All right, I do need to catch up on some of these comments here. Really great chat today, by the way. I appreciate everybody's time being here. I think I saw a question about what is IGV? Yep, right there. So let's answer that one. And all of these, a lot of this stuff are things that I go through and I discuss and talk about in Chiller Academy in the certification course. So like if you're wanting to have me go through a structured class where I really take you through this stuff, you can ask more direct questions and follow up and all that stuff, then I would encourage you just to go check that out over at chilleracademy.com. This is what I'm trying to teach over there. So what is an IGV? An IGV is an inlet guide vane. So inlet guide vane. IGV. Now what these are doing is we're talking about a centrifugal compressor. So we have an impeller that's running. It's a aerodynamic compressor, not a positive displacement. And we've got this ring coming into our impeller where we've got these little blades, little triangle blades. And there's all kinds of ways of how we can control these with linkages and cables and armatures and whatnot. But the core of it, these blades are affecting how this refrigerant is allowed to flow to the compressor. So if I do a side profile of a compressor, okay, so right here would be our IGV. Okay, this would be what this would look like if you're looking from this way in. And then back here would be the actual impeller. And of course, that's mounted on a shaft going to the motor. We have the back of our rotor housing, yada yada. So our suction gas is coming into our suction cone. We're going through the IGVs, inlet guide vanes, and then into our impeller. Now, if you're used to working on York, they're going to say PRV for pre-rotation vane. It's the exact same thing. They just call it something different. but we can open and close these IGVs in order to affect how this refrigerant is entering into our impeller. And by doing so, we're changing how much capacity, how much compression is going to be applied to the refrigerant. So from just a very basic high level, that is the core concept of your IGVs. Now there's a lot of other parameters that go into it. Like at startup, they need to be full closed. If we're going into a surge condition, then we want to try to close these off. And let's see. This is also part of what we're going to use for capacity control. So if we're going to be running off a leaving water set point, these will be varied open and closed to help the compressor maintain a specific leaving water set point feeding into the load. So this is what your IGV is, just as a whole, as a core concept. I can show you a picture of that here. I don't have one pulled up already. So let's pull up a picture of an IGV. Give me 1 second. Oops. Did that wrong. Try that one more time. So here's your IGV. All right. This is going to be the back side. You can see the armature connections here. And these are your little triangle blades. So they will pivot to open and close on a 90-degree turn radius. And it will then feed through this into our compressor impeller. So, yep. Good question. All right, we got a little more time. Yeah, it's all right, Keith. Yeah, I was thinking you were thinking it was low pressure, but no, yeah, it's a 134 high pressure. It's a 19XR by Carrier Centrifugal. They're the high pressure machine. You've got a leak. What's the hardest thing? The difference between cooling tower. Meter. Yeah, so I'm just trying to catch up on this chat. So the diagnostics or electrical faults. Yeah, wow. The hardest part is things to learn. Yeah. Oh, Tejas. Sorry if that's not how you say your name, but yeah, there should not be sweating. That's right. There should not be sweating on the compressor of a TurboCore. I do not want to see that compressor sweat. Yeah, especially in the electrical section. Like, I do not want to see it sweating. That makes me concerned that there is, like, you've got that refrigerant feed issue. Now, Benny, I see you've got a few questions here, so I was just trying to catch up on a few. All right, so the difference between a cooling tower and a condenser, or a chiller. this. There we go. All right. Clear my whiteboard here. What's the difference between cooling tower versus chiller? So they both cool water. From a fundamental scale, from that perspective, you could have an argument that, well, if a chiller's job is to cool water, what we actually define a chiller to be is it is a refrigerated circuit that is using a hydronic evaporator. So that's where we can get into a water cooled or air cooled on the condenser side. So that just changes whether we're using water or air to operate the condenser side of our chiller. But yeah, when you reference a chiller, we're talking about a machine that has a refrigeration cycle. It has a compressor of some kind, and we're using that cycle to cool an evaporator that has water or brine flowing through it so that we can process a load. That load could be an air handler for comfort cooling. It could be a CNC machine or some kind of manufacturing process, or cooling vats like in the dairy. So dairy and beer or breweries, we would use, we have to cool those vats down during their different treatment cycles, or like dairies after pasteurization. So in that process, that's what we're going to be sending that water or brine solution to in order to process that load down. Now, your cooling tower, on the other hand, it doesn't have the only refrigerant it's using is water, which is R718. That is water's refrigerant factor, or refrigerant number, I should say, not insulation factor. My bad. Anyway, so with the cooling tower, we're using water and ambient air to cool water, really, through an evaporative process. And that could be an open loop, it could be a closed loop. So depending on the style of tower, so if it's an open loop, then we're using the actual water that goes through our equipment, like the chillers, to flow out into atmosphere and evaporate the heat out of itself. That's what the cooling tower's main function is doing, is it is giving a place that that water can evaporate off, and that evaporation process is releasing a lot of the heat that water is holding. And so the liquid that stays behind is cooler, and the vapor that comes off gets just ejected into atmosphere. Now, if it's a closed loop design, well, then that water that's going through our chillers is not going through atmosphere. It goes through its own heat exchanger. But there is water in that cooling tower that is being flown over the heat exchanger, and it's the same evaporative process. We're using that water over that heat exchanger. The water in that heat exchanger is going to be warm. As we have water hit it, we flow air and water. That water begins to evaporate. The heat's carried away, and we cool the water inside the heat exchanger, which then goes back to our chillers. And then the water that's in the tower that does get exposed to the atmosphere just cycles through the tower constantly until it eventually gets evaporated out. So that's the basic process between an open loop and a closed loop. And with that, we're limited to the evaporative process, which means also being limited to wet bulb. So we can only cool condenser water as low as our wet bulb is. If that means we have an 85-degree wet bulb for some reason, that means the coldest our water can ever get, not even accounting for tower approach, which is a whole nother subject. The coldest that tower can get is 85 degrees with an 85-degree wet bulb. So that is the core difference between a cooling tower and a chiller. It's the equipment design, how it's used, and what it's used for. In a similar way as to why we call a chiller versus a traditional, say, RTU, rooftop unit. We wouldn't call it a rooftop unit with scroll compressors and an air over evaporator a chiller. That's not the terminology we would use in the industry. So in the same way, that's why we separate a chiller from a cooling tower. Um, when you get your suction imbo, yeah. Yeah, right. So that all should be insulated. That's right. On that TurboCore. Spend less than you earn. Invest. Yeah, there you go. That's a good. Uh, I like where you went with that, Mike. That's a good. That's a good direction, right? Yeah, it comes back to what do you invest in? You know, um, where do you invest your not only your time but your money, right? Both of those matter a lot into the kind of life we can build for ourselves and what we get out of it. So if you're a heavy spender, don't expect to have money laying around. It's just not going to work that way. Yeah, I should not be thinking of getting wealthy while being in a trade, but to enjoy the journey and what you do. Money helps, but will not give you happiness, and it won't. Right now, you could make the argument that well, money can give you the freedom to not have as much stress in your life. Sure, maybe to a point. And that's a whole philosophical thing that we're 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 chiller guys, right? Um, Not too worried about getting into that today. Question. I only thinking of wealth. As inflation rises and I have bills, I'm thinking of wealth and I'll be happy laughing all the way to the bank. I mean, enjoy your bank run, bud. Save some for the rest of us, I guess. Question. I only work on air-cooled chillers. Train, CGAM, RTAC. Are centrifugal or TurboCore oil-free systems the future? Should I start learning that and change jobs? I feel like I hit a plateau. Yes, with a caveat. It's not quite just a here. Let's get into it. This probably be the last question for the day. Okay. Let's get this loaded here. All right. And this is a really good point. This is something you really should consider. I do talk about this in the mag bearing section. So I do have a whole module in the certification course where I just go over mag bearing machines, their fundamentals, and I talk about just the future that I think we should expect with with mag bearing technology becoming what it is. So I only work on air-cooled chillers, Train, CGAM, and RTAC. Are centrifugal or TurboCore oil-free systems the future? Should I start learning that and change jobs? I feel that I've hit a plateau. I absolutely advocate for learning mag bearing machines. It's still early enough. Now, there's a lot more people that work on them than there used to be. I was fortunate that I learned mag bearing equipment, and I started that process very early on. It wasn't intentional on my part. It was just the environment I was in. I was in front of a lot of it, and I had to just learn it in order to do my job at the time. But what that did do is it opened up a huge swath of opportunities, and just it's been a huge part of my success in my career, is because it's a challenging thing. A lot of guys are really scared of it. You know, mag bearing machines have done to the chiller world what VRF has done um, to the comfort cooling RTU split system world, where people are just scared of it and they don't want to touch it, they don't want to break it, they don't understand it. It's a whole nother level of electrical and mechanical operation that it's just so radically different than what they're used to. They're fearful. It's just the only way I can think to say it. They're just fearful of it. And that's benefited me immensely throughout my career. So I can say, from at least that bias on my side, it's still early enough. Absolutely. And everybody's coming out with more of this technology. York has developed their own mag bearing that will operate in an air cooled. So it's not the same as their water cooled mag bearings. They have those too, and they've actually got two versions of those now. And they're not exactly the same. They are different in their own ways, but they're built for different applications. So you just from an air cooled perspective only, TurboCore has already been heavy in the market, and that's just with their TT series. Now, TurboCore also has other series of compressors that I think are going to also continue to compete further. Now, then you get into York's particular design, and Trane has heavily committed to Arctic Cool, being the fact that they bought them, and they're using TurboCores heavily. Multistack is using TurboCores heavily. TurboCores have been a very popular retrofit option for a lot of screw machines. Like, I've seen plenty of machines that were retrofitted with TurboCores from a screw. The screw compressor was taken out, the system was cleaned up, purged of oil. It's a whole process to do this, but then you can install a TurboCore in its place, and they've gotten good enough that they can manage the higher lift capacities, which was always the struggle. So here's the thing. The thing that was holding centrifugals back from being in the air-cooled market for a long time was that they struggled maintaining the lift that air-cooled environments see. They have much higher lift than a water-cooled environment would see, right? So typically the max top end we would see on a water-cooled entering is 85, 90 degrees maybe, whereas air-cooled, I mean, it'll get over 100 degrees entering into the coil. And then you add your saturation DT on top of that, your differential temperature on top of that ambient, and that pushes your lift so much higher, right? So it was the TurboCore and now these proprietary compressors coming in from the manufacturers who have now bridged that gap. They've invested into this far enough to overcome that. I do think it'll be high end for a while still. You're going to see this on the high end systems. Now, you may see some TurboCore on low end, don't get me wrong, but these specialty ones will be on the high end for now. And over time, just like we've seen with so many other applications, we're going to see that mag bearing move into the standard and low end market. We saw this with mag bearing water cooleds. Mag bearing water cooleds were these high end niche applications that we did not get into very often. But then, with time, the market adopted them. They became more reliable, and now they're an active part of every conversation you go into. Do we go mag bearing or not? And it's getting harder and harder to find plants that don't have a mag bearing in them. And they're now making mag bearings in larger sizes too. So that was the thing. They only fit into a narrow window of equipment sizes. Now they're like the YZ specifically by York. That chiller is made to scale so that it can scale into those larger sizes and compete with those bigger chillers, in addition to having their YMC squared also compete on the lower side. And that's kind of the difference. Like the YMC squared was not built to scale to a large scale, but the YZ was. And that's kind of how York has positioned those two. And that's, now that, again, that's water cooled side of it. And if you're focused on the air cooled side, the air cooled market has been impacted and will continue to be impacted. That is my opinion and my assessment based off of what I see with what the manufacturers are coming out with. Take Daikin as an example. They not only do they have their high pressure mag bearings, now they've released their low pressure mag bearing, the WMT, right? That's a low pressure a centrifugal magnetic bearing machine. Trane has their agility chiller now, which is the WHD, I think, is the model for that. Again, that's a competitor to York's YMC squared. The Trane needed something that could compete against York, and that's what they came out with. And it's, again, a magnetic bearing centrifugal. So if it's mag bearing, it's going to be oil free. And how about this? It doesn't make sense to put an oiled centrifugal in an air cooled because of efficiency losses with the oil. Like, there's just too many problems. It's far better to go with a screw compressor. But once you remove that oil from the equation, so all of those are going to be oil free. All of those air cooleds are going to be oil free if you see one that's an air cooled centrifugal. Long story short, I would highly recommend it. And you're not too late. There are most people, while they're less scared of mag bearing today than they were 5-10 years ago. They're far less scared of it today. Most technicians that I talk to still severely struggle properly working on and communicating around a magnetic bearing chiller, which means you have immense opportunity that if you can get in there and figure it out, you can fill that gap and really do well for your career. Yeah, I appreciate that, man. Happy to help. And money, I was born with the last name. What can I say? Do you think the new oil-free Copeland compressors will compete with TurboCore? No, I don't personally. I think those Copelands are. They're trying something using the airfoil technology. The problem I've seen with those bearings is that they're high maintenance bearings. And when you look at applications of what they're used for outside of what Copeland is doing, I think Copeland is taking a Hail Mary because they're trying to get into the game, but they can't copy everybody else. And I don't think they have the engineering to produce a centrifugal that can compete with these other guys. I really don't. I don't think they have the engineering for that. They haven't proven that they do. So I think they developed this aerofoil, and they've had amazing marketing around it. Don't get me wrong. They've done a great job of marketing. Copeland is good at marketing. But I do not have faith that their compressors are going to do well long term. I think they're great on the showroom floor. Heck, at AHR, they had a chiller there, air-cooled chiller, running a set of them. It's cool. It's great for the showroom floor. I challenge it in the real world environment. Copeland is welcome to prove me wrong. But looking at how they designed that bearing and what they're doing with it, to me, it's a short shelf life. I think they would have been far better going mag bearing. And they didn't want to go mag bearing because so many people are scared of it and they struggle with it and they don't want to, they're cautious to touch it because it's so hard and so expensive to work on. I get why they didn't want to go mag bearing. It's a very difficult road. So with theirs, you eliminate all of those extra electronics. But I don't think that a foil bearing was the solution. I do not think that was the solution. And every single time that compressor goes to start up, that bearing and shaft are running on each, like that shaft is making contact on that bearing surface every time it goes to turn on. And these are high speed machines, high speed. And so now they kind of have to be in order to create the bearing surface. And we don't have time today necessarily, but maybe next stream we can get into that Copeland compressor more, and I can talk about just my thoughts around it and kind of draw out more of what I'm talking about, so you can understand where I'm coming from. Anyway, no, I don't think it's going to compete that much with TurboCore. I think it'll have a good stint, and Train went through this with their RTAE. RTAE had a horrible launch. Major parts issues. They chose bad condenser fan motors. They just, in so many ways, that model turned into a flop. And they had to go in, fix it, and relaunch it as the RTAF. So the ones they're selling on the market today are the RTAF. It's not going to shock me whatsoever if we have a similar situation with Copeland, where people try it and then they just don't hold up. Like I think, because I didn't even see anything in there that was going to control thrust. Like, again, I'm going to get off on a spill here, but not only are you allowing your shaft to make bearing contact at startup and spin down, because as soon as that compressor gets below a certain threshold, it can no longer make lift for itself off of the foil. So it's going to make contact and finish spinning down. So that's friction force right there. Then you get into a surge condition where you've got thrust either way. Well, yeah, you've got a dual impeller or dual head shaft or an impeller on each side. So they have counteracting forces. But the thing is, you've got one stage feeding into the other stage, and those thrust forces aren't going to be perfectly balanced in a surge and high lift situation. Like, they're going to get unstable, and it's going to allow that compressor to shift back and forth. And I didn't see any mechanism in there that was going to control that axial thrust. Those foil bearings are only controlling the radial thrust or forces, not the axial forces. And the idea is, when the compressor is in a normal operating condition, it's going to balance that out via the dual shaft impeller, or dual shaft impeller, or impellers, the dual compressor design. Damn it, the dual design where there's an impeller on each end of the shaft, right? In perfect conditions, that balances, and it's not a bad way to do a compressor. We've done those kind of compressors for decades, oiled and oil-free. You know, the Daikin's WMT series is that exact design. It's a mag bearing, dual impeller, dual shaft, right? That's fine, but it's got a mag bearing, and so there's a set of bearings in there that are dedicated to radial loads, and there's a set of bearings in there dedicated to axial loads, and they control all of those thrust parameters. Like, that's under control, and it's going to be balanced most of the time until it's not. With everything I've seen from Copeland, they don't have those mechanisms. So what that means is, you get the wrong conditions, you're making a touchdown with that impeller. Prove me wrong, Copeland, but I don't agree. I don't agree. That's not my whole rant, by the way. I'm stopping myself there. I love the question, though. I love the question. The refrigeration in grocery stores. I see the lioness is in the chat. Miss Schamberger, Miss HVAC Time herself. I would pay for what I do. Oh. All right. Yeah. So I'll say here, buddy man, if we're here to just argue and be disruptive, bud, you don't need to be here. Okay? I can say that publicly here. So if your interest here is not to be a genuine contributor to the community here, you're not actually interested in being a part of what we're trying to do on good faith, and you're just looking for ways to stir up stuff, then just don't come back. Okay? We don't. That's not the kind of attitude. That's not the kind of environment we're going to have. If that means I need to block you from the channel to accomplish that, I can do that. But coming in here just to start arguments for the sake of, I'm not going to have that in my chat. All right. Okay. I see their gearheads. I appreciate it, bud. I really appreciate it. Okay. Well, I think we're going to call it there. Y'all have a great week.